Hi everyone, with this video I want to do a quick introduction to classification and just give an overview about what we're going to be talking about over the next couple weeks. So classification is a bit different, I think, than what we've covered before. I think it's quite exciting, and as I mentioned in class, this is an active research area and a lot of companies are heavily using this in a lot of their products. So I think finding motivation for classification really is not needed, but maybe I'll give you a little bit today and sort of help you out with that. So classification is quite simply, so in classification, our goal is to do what? Our goal is to do a prediction, and this prediction is usually qualitative. So we want to do a prediction, and this prediction is qualitative. So what do I mean by qualitative? Well, this is a big word, but really all this means is I'm predicting a label, right? So this is just a label. If we don't want to think about an actual label right now, you can just think of it as a label 0, 1, or really anything up to k. But as I mentioned in lecture, we're really in this class only going to be talking about binary classification, so 0 and 1. But our goal is to put people into groups, right? And this is not necessarily a number. This could be any label, right? So this could be determining who is a customer or who's going to buy a product. So who will buy a product? And that basically would put you into two groups, right? Someone who does buy the product, or who we think at least buys the product, and someone who does not buy the product. And same thing, rest here. And someone who does not buy that product. And you can really make any labels to this. And in class, remember, we had those examples. We were also talking about, let's say, a movie becoming a blockbuster. So in that case, our labels would be whether the movie becomes a blockbuster or does not become a blockbuster, etc. But this really is the overarching goal of classification, is we want to put people into groups, right? We don't want to assign a number, right? It's not like A/B testing where we're just trying to see if one group is better than another. We just want to put people into groups in the best way possible, right? And so there are a lot of really cool ways we can do this. Classification is just really so broad, and there's so many algorithms, and we're not going to get the chance to talk about all of them in this class. But I'd say we can break all classification algorithms into two groups. So there are two main groups. And I'll talk about what these are in a second, but the first one is the class of supervised algorithms. So what is a supervised algorithm? Well, a supervised algorithm is when we know the labels ahead of time. All right, so here we know labels ahead of time. And really, we don't need to look for the future. Obviously, we just need to know the labels ahead of time for some previous data. So some previous data. So what does that mean? For our examples above, that means that we know, let's say, what movies in the past were blockbusters, or we know what someone has bought in the past, right? And that's sort of what I mean by knowing the labels ahead of time. And then we have another class of algorithms that are called unsupervised algorithms. And these are very similar to supervised algorithms, but we actually do not know. This is very key. We do not know labels ahead of time. And this actually might seem really weird, and we're not going to get to this into the clustering section, but we somehow want to put people into groups without knowing what these groups are ahead of time. So this is, this here should be very interesting to you, so I'll just write interesting. And we'll get back to this in a little bit when we talk about clustering. But for now, we're going to be focusing on this type of algorithm, supervised algorithms, right, where we know the labels ahead of time. And that's actually quite nice, because if we know the labels ahead of time, we can look in the past and see what those groups look like, who we've assigned to those groups in the past, and try to do something similar in the future, right? Or pick a rule that sort of allows us to get as close as possible to what those groups look like. And before I go any further, this idea of having labels in the past and in the future and assessing how well our algorithms are doing relies on a really important concept that we're going to be using over and over again in classification. And this is going to be called the validation set approach. And I'll talk about this more in class, and I'm sure for weeks to come. Right? And so this is one way we might want to use our algorithms. We might want to assess how well they're doing. So the idea here is, let's say we're doing a supervised algorithm, and so we have a data set. I'll pretend like I can draw it in this big box, right? And this is our previous observation. So this here, this is just a data set of previous observations. And we have a lot of data here, so I'm gonna say we have data X, right? So this is our data, it's just a big X, right? Or maybe it'd be easier for me to write it like this. I have X1, comma, Xn. These here really, these are our features. Right. So, if we were trying to predict whether or not a movie's a blockbuster or not, these features could be things like the actors, how much money we've spent, what theaters are opening in, the genre, etc. Right. And then, of course, with every classification problem, we have a label, right? Because this is supervised, right? And we're going to call this label Y. This is generally how we do it. We call the features X and the label Y. There's no real reason for it, but this is just the terminology everyone goes for. And this label Y, in our case, is going to be the classes, right? And since we're dealing with binary classification, you might notice it's like a 1, 0, 0, 1, dot, 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 right? Something like this. And this tells us in the past, for some given set of features, right? So these features keep going all the way down for our entire data set. It's our big data set here. This tells us for some given features what their previous classes were. So for this person, let's say, or if this was a movie again, if for this movie, this would have been a blockbuster. Right? And this would have not been a blockbuster. So no, not a blockbuster. Right? And that's good. And we can use the results of these features to predict that. Right? But how exactly are we going to assess that? Right? We need a way of assessing how good our algorithm is. So in general, people break their data sets with some proportion, right? Let's just say we'll do it by half. So I'll draw another picture sort of demonstrate this. So I can have another data set. Maybe I'll just draw it over here. So I can have another data set, or let's just say it's the same data set. And let's say again, I have my Y's, right? Dot, 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 dot. And then I have my features, X1, Xn. And then I'm going to randomly split it. So let me just get this red here. I'm going to split it in half. I'm going to split it in half. And then I'm going to take the top half. So I'll color this in orange. I'll take the top half. And I'm going to sort of separate it from the bottom half. And I'll color this one in, let's color this one in green. And I'll separate it from the bottom half. And what do I end up doing? Well, this top half is going to always now be referred to as my training data sets. Okay, and what's the green one going to be referred to as? You might have guessed it already. It's going to be referred to as our testing data sets. Now, why is this useful? Well, we know in this entire data set what classes each observation corresponded to. But I'm going to do something kind of tricky. So I'm going to look at the training data set and I'm going to create a model. So I'm going to create a model on my training data set. right, so I'm going to create a model on the training data set. Let's highlight that so we don't forget it. And then what is step 2? Step 2 is I make a prediction. So I predict using this model here. So I use the model from step 1. So I'll write that. So I predict using that model from step 1, and I make a prediction on my testing data sets. And you might think, well, Brad, this is super weird. Why would I predict on a data set I already know the labels to? And you're going to do that because you're going to check how well your predictions actually, or how good your predictions actually were, right? So you're going to predict on this testing data set while ignoring the labels, right? So you're going to predict ignoring the labels. And that's actually quite nice because once you make this prediction, you can imagine in your data set now, you're going to have a bunch of true classes, and I'm going to call that Y. Maybe it's 0, 1, 1, 0, right? And then you're going to have your predictions from the model. I'm going to call that Y hat. These are your predictions. Maybe here you got it right. Here, maybe you made a mistake, and then here you got it right, and here you also got it right. So in this case, you can see the accuracy of your prediction was decently good, but you made a mistake here. Right? And this is one way for us to assess how well a model is performing, right? Because I sort of leave out some proportion of my data set where I know the truth, and then I ignore the truth and make a model, and I see how well my model performs on something where I know I sort of have an answer key for this. So this is quite nice. So the testing data set, you can think of it as being an answer key. I really like that. So the testing data has an answer key, right? But you ignore it when you predict. And then at the end, you grade yourself. And this is what we're going to do for all classification algorithms that we look forward to, that we're going to be learning in this class, for all of the classification algorithms that we're using. And I'll maybe talk about this more in class, and I can make another video about how to do this. This validation set approach is quite simple. So the validation set approach, I'm going to say it's simple because we only did 2 splits. But you can imagine that we can actually expand this and do a little bit better than just doing 2 splits. You can sort of arbitrarily do k splits and somehow average over all of these splits. You can imagine instead of having 1 split, you can have 1, 2, 3, all the way to k. 1, 2, 3, all the way to k. And then for each of them, you can use, let's say, splits. You use the first 1 to k minus 1 splits, and this could become your training. And then you can use the kth one, can be your testing. And then you repeat this k times where you keep alternating the split they're using for testing, and then you average over everything. We'll talk about this k-fold cross-validation more. Right now, I just wanted to let you know that it exists, and it could be a nice extension. But right now, just focus on this validation set. I think this is the most important thing to understand first. But just we know that there are probably bigger things out there. And then to sort of to finish up this classification introduction, let's go back to our original plot that we saw in class. You can imagine if this is a very simple classification problem, we might be able to draw it as a plot. In general, we can't do this because we have more than 2 features. But you can imagine we have something like this. Right? We have a bunch of green dots because that was the color I had. And then maybe we also have some red dots. Put some red dots here. Here. I'll put most of them up here. Yeah, let's do that. And then let's say we wanted to find a line that best, or classification rule that best separates these things. So we might have a classification algorithm that does that for us. So we imagine this maybe is a really nice line. Right? And so this would be an example of one of the first types of classifiers we're going to talk about in another video. This would be a linear classifier. Just to give a teaser on what I'm going to talk about next. This would be a linear classifier because the decision rule I'm making, which is this blue line, that decision rule is a line, right? And we're going to restrict ourselves to only looking at this line, which I think is actually quite useful because we know a lot of really good things about line. You might think of linear regression, right? This is a recall 310. You might think of linear regression as being a nice way of getting this line. It doesn't quite work out like that, but it should be coming back into your memory. So maybe there's a nice thing to do with just this linear model. And we're going to talk more and more about this. And obviously, as a teaser, I'm not really going to get into in this class. As I mentioned, you could look at different classes of classifiers, ones that are not lines. You could arbitrarily draw a line that sort of perfectly separates this entire something like this, right? Something like that. Something that perfectly separates everything. So here you would have 0 mistakes if you had this arbitrarily squiggly line. So this arbitrarily squiggly line gives us 0 mistakes. And so you might wonder, Brad, why don't I always use this arbitrarily squiggly line? And I'll get into this more in class. Just to finish this video, you might imagine, one, this is difficult to estimate because it's so squiggly. And the second thing is this might lead to overfitting. And again, I'll talk about this a little more later, but just so I can motivate why these linear classifiers are really nice. We don't want to overfit because the thinking here is if we look too much like the training data, it might not expand well to a population. So I'll leave this thought with you as we're finishing the video. That looking too much like our data could be bad. And we'll talk more about why that is in the future. But I hope this has been a nice introduction to classification. And if there's any questions about this video, please let me know.